Because what you don't want to do is you don't want to reinvent the wheel. So a lot of, like for example, the CDC has done studies. Oh, this is cigarette smoke. But combustion products of synthetic materials such as plastic contain cyanide. And, it could contain hydrogen cyanide. Hydrogen cyanide is the gas they used in the gas chamber to execute.
What? Oh, yeah. So burning plastic?
Yeah, burn. So you have to be careful. You just don't want to burn it, especially out in the open. You want to burn it in the hood, or you want to be able to catch it. Firefighters would have to know about this as well because
there are houses that are burning up.
Hydrogen cyanide, the real killer among fire gases. So check it out. There's a lot of studies about the fumes from melted plastics or the products from melted burning plastics. I know people burn rubber all the time in our lab, and it stinks up the whole lab.
Is that dangerous?
It's not good for you. It's a health hazard.
Did you hear that there's countries that'll burn that have like that illegally just burn plastic?
Yeah.
Yeah.
Other nations send them plastic so they can burn it.
Yeah. I mean, there are lots. They burn the boards to recover the metals. So they try to burn like electronic boards, and then they can recover the gold and copper and whatever other metals they have on it. But it creates a lot of pollutants, so that's a serious concern. And those pollutants end up causing a lot of damage. Anyway, let's take a look at this because you know the products of burning plastics is a mixture of gases. So we're still on mixtures of gases here. A scientist sets up an artificial atmosphere with 4 gases. The partial pressures are 0.78 bars of nitrogen. And so this is a constant volume thing, so we can just do it in one container. And so we have 0.78 bars of nitrogen. And the volume of nitrogen is the volume of the entire container. And then we have 0.21 bars of oxygen. So what kind of artificial atmosphere are they trying to create? Yeah, it's like air. And so 0.21 bars of oxygen. So the volume of nitrogen, actually the volume of this atmosphere is equal to the volume of the nitrogen, which is equal to the volume of the oxygen. You know, the oxygen can go anywhere in this container it wants. Same with nitrogen. Nitrogen can go anywhere in this container it wants. Then we have 0.009 bars of argon, the minor component, 0.009 bars of argon, and 0.025 bars of water vapor. And so this is humid, at least. There's a little bit of humidity here. It's not totally dry gas. And so what is the total pressure?
Just add them all up?
Yeah, we just add them all up. And so this is an example of Dalton's or Avogadro's?
Dalton's.
Dalton's. So we use Dalton's law, which is shown here. Just add it up. It comes out to 1.02 bars. Here they're trying to show something else here. What they're trying to show is they're going to take 1 liter of nitrogen plus 1 liter of mixture. So if 1 liter plus 1 liter equals 1 liter, then this is constant volume, which is Dalton's. And so all we do is we just add up the pressures. So this is going to be 186 millimeters. That's 93. So 186 plus 93 gives us 279.
Does it have to be in a specific unit? ATM or?
No, any unit is fine. It doesn't have to be in any specific unit.
As long as the volume.
As long, yeah, they got to be consistent. As long as the volume's constant. But I don't like this because is the volume really constant? They say 1 liter, 1 liter, 1 liter, so it appears to be constant, but what's happening with the mercury level, it's different, therefore the total volume is different. So this is not good.
It's not accurate.
It's not accurate. What's that?
What portion are we supposed to be looking at that proves that the
The
volume is
total,
different?
the volume of the green gas here is a little bit bigger than the volume of the red gas here. Maybe it's different than the volume of the mixture here.
So they're all supposed to be exactly
Yeah,
like
they
lined
should,
up across?
no, they should all be the same volume, and they shouldn't have used a manometer for this. They should have used it like a pressure gauge, like something that doesn't change the volume. The manometer changes the volume quite a
So
lot.
it's because of how much it pushes down?
Yeah, right.
Maybe we can't tell if it's with the knob.
Yeah.
Well, no, aren't the numbers at the top different anyways too, like the moles? Like this one's 0.01 moles, and this one's 0.050 moles?
Yeah.
Shouldn't they all be the same number?
No, it could be any number you want. So there's twice as much nitrogen as there is oxygen. The total is 150. Out of that, 50 is O2, 100 is N2. And so what we say is that this is 1/3 oxygen, 2/3 nitrogen. So in other words, it's 33% oxygen, 67% nitrogen.
So this one is not like the other one that we did, where the volume is the same.
Well,
Like where
this-
we had 100 liters of air, and then 100 liters of N2, and 100 liters of O2.
It's supposed to be the same.
So is that something that's wrong too?
No, that's right. This is the same problem that we were looking at earlier. If I took 1 liter of mixture, that 1 liter of mixture, which consists of nitrogen and oxygen, would be 1 liter of nitrogen and 1 liter of oxygen. If I look at 1 liter of nitrogen, it's got to be at a lower pressure.
So moles is different than liters, right? So
Yeah.
moles would be N, and then liters would be the B, and this one would be a constant B.
Constant B, yeah. Okay, here's another mixture. This KCl3, do you know what the KCl3 is called?
I don't remember. I don't remember the last time I did it. Like my science literally is don't sit there. I was thinking, I get a lot of good ideas.
Potassium chlorate. Potassium chlorate is correct. Potassium chlorate is unstable when heated, and it decomposes into potassium chloride and what else? And oxygen.
That was an experiment.
So if we balance this, probably the easiest would be 2 KCl3s goes to 2 KCl's plus 3 O2s. This is a way to generate oxygen gas. Compose this. So you see KCl3, when we decompose it, it's a bit slow to decompose. So they add a trace of MnO2 as a catalyst.
Just speeds up it.
It speeds up the reaction. Yeah.
Manganese.
KCl.
Oh, yes. Potassium chloride. We're gonna watch the video?
We'll just watch a little bit of this video. All right, so they're decomposing some potassium chlorate, and they put some food color in the water. This is just water here. And the oxygen is going to fill the neck here. As it fills the neck, it's going to push the water out of the flask. There's this tube here that's open at the bottom, and it's going to force the water into the cylinder over here. And so they're going to do this with catalyst and without a catalyst. So here they're,
So the blue coming out is water?
yeah, it's just food color in water.
Oh, just.
Let me speed this up.
Was
So here, potassium chlorate, they're melting it there, and you can see some bubbles of oxygen gas. You see it? Some bubbles of oxygen gas form.
why doesn't the gas go into
The gas is coming into the neck, so do you see the level here is dropping very slowly? It was up here, and now it's going down.
But why doesn't the oxygen go up into the tube instead of?
Well, the oxygen's coming in here, and so what it's doing is it's forcing the water down, and then the water can escape. There's another tube that's submerged in here that's open, and the water will escape that tube.
Oh, okay.
So what's left inside the test tube?
I'm sorry?
What's left inside the test tube? Oh, that's-
Magnesium.
KCl. So actually, there's still a lot of unreacted KCl3 because it took 2 minutes to generate about 20 milliliters. Now they're going to put some of this black MnO2, just a little bit, a quarter gram of black MnO2 and mix it. So it looks like that. It's actually black MnO2 and white KCl3. Now look at when they heat this up, look how much faster it is with a catalyst. The same reaction, but now we can visually see this drop. It hasn't really started yet.
There it goes.
Okay, there it's going. Now you can see.
Oh, yeah, look at it.
Do you see the level drop?
Yeah.
Yeah.
So they're forming a lot of oxygen gas there. It's forcing the water out of the flask through this tube here, which is draining here. So you can see that generating a lot of oxygen there.
That's smart. You can measure how much
No, it's better with
oxygen.
So the question is this. Is this pure oxygen that's being generated here?
Maybe.
Yeah.
Let's see the formula.
Yeah, this is it.
Yeah.
We should be generating pure oxygen, but do you know what's captured there is not pure oxygen?
What is it?
It's contaminated. Do you know what it's contaminated by? Because we should just be generating O2. It's not balanced.
Is it contaminated by the catalyst?
No,
Whatever they added. What was that thing you said? The black, it was the black.
that's the catalyst. It wasn't contaminated by the catalyst.
Yeah.
By the food color.
Yeah. It's a mixture of, it's like another compound.
The food coloring contaminated.
The food coloring didn't contaminate it. You know what contaminated it? This oxygen is not pure here. You know what's contaminating this oxygen? Water. Water is contaminating it. Because what's going to happen is some of the water is going to evaporate off the surface and humidify the oxygen. And so the oxygen is not totally pure. If it was totally pure, it'd be dry. And instead, it's going to have some humidity. Now, how much humidity does it
Where
have?
those hydrogens come
It's water. It's not hydrogen.
from? Water is H2O. No H's in there.
I know there's no H's there, but this apparatus is used to capture the oxygen. If there was no water here, then we wouldn't contaminate it. But there's water here because it makes it easier to capture the oxygen here if we just bubble it through the water or force it down into the water.
Oh, so that water was just part of the experiment.
Part of the experimental apparatus. It's not part of the reaction. And so this oxygen,
100% water.
what we say is this oxygen is wet. It's wet with water vapor. And so we don't have pure oxygen in here. We have oxygen, which I'll have as black here. This is O2 gas. And then some of the water molecules are going to evaporate off the surface. This is called vaporization. And so as the water molecules vaporize off the surface, they're going to contaminate my oxygen gas. And this is going to be H2O gas, water vapor. Now, how much water vapor do I generate? Well, what we're going to say here is we're going to generate the maximum amount of water vapor here. The maximum amount of water vapor here is going to be, because the oxygen's bubbling through the water, is going to be when the oxygen's saturated with water vapor. When the oxygen's saturated with water vapor, then we call that 100% relative humidity. Is it 100% relative humidity in here?
Oh.
No, it's way less. 100% relative humidity would be really uncomfortable. So if you're stuck or trapped in here, you'd really notice the humidity.
Did you drown?
If you, I guess, yeah, you could drown if you.
You drown in air, huh?
I don't know.
Yeah, you
How can you drown in air?
If it's really wet,
Yeah.
while you're breathing in, and then you're breathing out.
Can't you
Yeah.
get air? Walk in your lungs?
It doesn't feel like you're drowning if it's that humid.
Let's do an experiment so we could drown something in air.
All right. Well, 100% relative humidity, it would be like an indoor swimming pool. Indoor swimming pools would be 100% relative humidity.
That's what it's there for.
No one.
That's certainly a purpose.
And so let's look at this process here for humidity. So I'm going to jump ahead here. And so the way we're going to achieve 100% relative humidity is we're going to cap this. If this were open, then we could eventually evaporate all this out if the lab wasn't very humid. And so we're going to cap this so that we can saturate the gas in here with water vapor. And that process is going to be due to vaporization. The vaporization of the water molecules off the surface. Okay, not only can the water molecules vaporize off the surface, if they come back, they can condense back to a liquid. And so that's what these down arrows represent, condensation. And so it looks like we have more up arrows. If we have more up arrows, then there's more vaporization, and that means the humidity is increasing. And then we have down arrows. If we have equal amounts of up arrows and down arrows, then we've saturated it. That is, we've reached 100% relative humidity, because the number of water molecules vaporizing off the surface will equal the number of water molecules sticking back onto the surface of the liquid. So we'll take a look at.
Would the evaporation decrease the volume?
Yeah. Evaporation will decrease the volume. So if we have dry gas, if this is dry gas, then the only process is evaporation. As the gas gets more and more humid, more and more wet, then we're going to have condensation start. But the condensation is relatively slow because we don't have that many molecules here in the gas phase. But the more molecules we have in the gas phase, the more the condensation rate grows. Eventually, the evaporation and condensation rate equal. When that happens, there's no further change. And so what we have here is a net evaporation, because the evaporation is greater than condensation. And then once condensation speeds up to this point where we've saturated it, then it's stable. The only thing that could change it is by changing the temperature. If we increase the temperature, then we can get more vaporization and we can increase the humidity. If we decrease the temperature, we could get less vaporization and decrease the humidity. And so we can increase the rate of evaporation by changing the temperature. That's one thing to do. So we're going to look at One thing is, what's holding the water molecules together in the liquid? Is it gravity? This is a water droplet here, so we're looking at the side of a water droplet. Here we can see some water molecules evaporate. There's one that condensed there. Here's some that evaporate. So we see evaporation and condensation. When the evaporation rate is equal to the condensation rate, then we've reached 100% relative humidity. When the evaporation rate is greater than the condensation, then we're less than 100% humidity.
So evaporation rate is equal to,
Yeah, at 100% relative humidity. Now, what's going to change the relative humidity is changing the temperature. Here, the temperature that they have is 370 Kelvin or 97 degrees C.
Behind the lecture.
so what's equal to the evaporation rate that makes it, it's like how much
Yeah,
of the
when the evaporation rate equals the condensation rate, then it's saturated. We can't put more water in there.
Condensation and
Yeah.
evaporation.
Yeah.
When condensation equals evaporation, you have 100% relative humidity.
You can see the motion of the water. What are the water molecules doing? They're vibrating. They're translating and they're rotating. So those are the three motions here. What holds the water molecules together are what we call intermolecular forces. The gases, the molecules aren't held together. The gases, the molecules are in random, what we call straight line motions. Sometimes they get close to each other and they might form a dimer, but that's not permanent. Like if two water molecules get close enough, they might kind of stick together for a short period of time before they're broken apart. But over here in this droplet, all the water molecules are being held by intermolecular forces. The intermolecular forces give the water molecules stickiness. That stickiness arises from electrical attractions. The electrical attractions come from the dipole of water. The oxygen end of water is negative, the hydrogen ends are positive. So the oxygen end is attracted to the hydrogen end of water. So that's vaporization of the surface.
So when is it going to be equal so we can see relative humidity?
Oh, this is equal. That was equal.
That was equal the entire time?
Yeah. Here, this is unequal. This is formation of a drop of water. This occurs in clouds and fog. And so here the air is saturated with water vapor, so we're going to see net condensation. There's no evaporation occurring here. No, this is really humid air here. It's saturated. Maybe it's been super saturated with water. There's too much water in this air to sustain it. Here's a small cluster of water molecules being held together by intermolecular forces. And so this is like a baby droplet, and this baby droplet can grow into a bigger droplet. These small clusters are unstable, so they can break apart, or they can nucleate into a droplet.
Where is it? I mean, how they film this? In the sky at night or something?
No, these are all like Disney-like animations. These aren't real. It's just, but it's not totally fake either. These are like, these are based on quantum mechanics. A lot of computer time went into this. It's like supercomputer time.
I showed that to them. I told them about it. They're all clean. They use film. I'm on an organic diet. There's larvae. Where it turns into
All right. So the situation is whenever we collect a gas over water, that gas is going to be contaminated by water vapor. How much water vapor is in the gas depends on what we call the vapor pressure of water. The vapor pressure of water depends on the temperature. And so the total pressure in this gas is equal to, actually the total pressure of the gas mixture is equal to the pressure of the gas plus the pressure of the water. We can find out the pressure of the water from tables. These are called vapor pressure of water tables. Here. So at low temperatures, the vapor pressure is pretty low, 6.5 millimeters of mercury. At high temperatures, the vapor pressure goes way higher. For example, at 100 degrees C, the vapor pressure of water is 760 millimeters of mercury. So quite a bit higher. And so the humidity, at 100 degrees C is going to be much higher than the humidity at, say, 5 degrees C.
So to know that one, we need to know what temperature we were heating the.
Yeah, we need to know the temperature. But both of these are 100% relative humidity. So at 5 degrees C, the air can't hold that much water. At 100 degrees C, the air can hold a lot more water. Well, the air can always hold a lot of water. It's just maintaining that by the temperature. All right, so let's take a look at an example here. Problem. Okay, calculate the partial pressure of oxygen in atmospheres in a sample collected over water, given that the total pressure of the mixture is 0.98 atmospheres, and the partial pressure of water vapor is 16.5 millimeters of mercury. 16.5 millimeters of mercury means what temperature must have that been? Let's take a quick
Let's
look.
look at the chart. Let's look at the chart.
Yeah, we look at the
That chart
chart.
is provided for us?
Yeah, this chart would be provided for you. But 16.5 millimeters would be
Between, it's on 17.
17.
Yeah,
No, it would
no,
be
a
closer
20.
to 20, so it'd be like 19 or 18.7.
Well, 16.5, so it's between 13 and 18, something like that. It's 16.5. What we need is a better table.
I know in the book somewhere.
I'll show it you right. I'll tell you right.
That was better?
This is in kilopascals.
I think he just.
Are we going to be getting a chart? Oh, wait. We're doing part 2 of the lab. Are we going to be doing a lab on that?
On this? Yeah.
But not this week, next week?
Well, I have to take a look. All right. So anyway, in this particular problem, the total pressure of the gas is 0.98 atmospheres. So that's the pressure of the mixture, which is equal to P total, which is equal to 0.98 atmospheres. All right. So we have a total pressure of 0.98 atmospheres, which consists of this gas. I don't know what the gas is, plus water vapor. The pressure of the water vapor is 16.5 millimeters of mercury. And so what we have to do is we have to get these in the same units. So we either need to convert atmospheres into millimeters of mercury or millimeters of mercury into atmospheres.
Millimeters of mercury in the atmosphere.
Yeah, and so they convert millimeters of mercury to atmospheres. So 16.5 millimeters of mercury, that's the pressure generated by the water molecules here colliding with the wall, is 0.0217 atmospheres of H2O vapor, or H2O gas. And so what is the pressure of the gas? Well, the pressure of the gas is this. P total of the P of the mixture is equal to the pressure of the gas, the dry gas, plus the pressure of the water vapor. The pressure of the water vapor we call the vapor pressure of water. And so it's going to come out to this. Well, we don't know what this is, but we know what the total pressure is. So the pressure of the gas we can solve for is equal to the total pressure minus the pressure of the water vapor.
The total pressure is 0.98.
Yeah.
Let me subtract the points. That's simple.
So it comes out to 0.096 atmospheres. So those are gas mixtures. Now we're going to move to liquids and take a look at the time here. When we look at liquids, we're going to look at some of the common properties of pure liquids, liquid mixtures. Do we use it? Yeah, we can use it for liquids too. So some of the key differences between gases and liquids: gases may be compressed. Gases consist mostly of empty space, so you can compress them. You can also expand them. Liquids cannot. You know, the particles that comprise a liquid are touching already, whereas particles in a gas don't touch each other. Gases expand to fill their containers, liquids don't. Gases have low density, liquids have high densities. And so the gas, like for example, of H2O gas, its density would be like 0.001 gram per milliliter versus water, which would be 1 gram per milliliter. Gases may be mixed in a fixed volume. This is why we can get 1 liter plus 1 liter. It gives us 1 liter, or 100 liters plus 100 liters gives us 100 liters. You can do that with liquids. If you take 100 liters of liquid A plus 100 liters of liquid B, it's not going to come out 100 liters.
And 200 liters.
It'll come out like 200, yeah. Gases exert constant pressure on the walls of their container uniformly in all directions. This is true for small scale, but if you do a large scale, then, you know,
It's harder.
yeah, because let's say if you're looking at the atmosphere, what has higher pressure? The bottom of the atmosphere or the top of the atmosphere?
Bottom.
The bottom, because it's pressing. It's just like water then, in that sense. It's going to weigh more at the bottom than at the top. But they're saying it's constant, so they're saying the top has the exact same pressure as the bottom. Well, that's only true for small distances, you know.
Moving different here to the sky.
Yeah. Okay, pressure in a liquid container increases with increasing depth. For liquids, it's easy to tell, you know, the difference in pressure. Right, these are some of the properties of liquids. Most liquids will exert a vapor pressure, and vapor pressure is due to evaporation. It's a liquid vapor, like water vaporizes. Some things vaporize easier than others. Like water vaporizes pretty easily, but what about something like maple syrup? Does maple syrup vaporize very easily?
Maple syrup has sugar in it, so,
Yeah.
right?
Yeah, maple syrup is really sticky.
So I don't think it's gonna vaporize.
It doesn't vaporize easily, and so those are due to the stickiness of the molecules, or what we call the attractive forces, or the intermolecular forces. The stronger the intermolecular forces, the less vaporization we have, and the lower the vapor pressure. So maple syrup has low vapor pressure. Water has much higher vapor pressure. What about gasoline?
I think that's a low vapor pressure.
Low vapor pressure?
Yeah, I'm pretty sure gasoline.
Does it
Water
burn by it?
Well, does gasoline vaporize easily, or?
Yeah.
Very.
Or how about alcohol?
Oh, alcohol is very
yeah.
low.
Yeah.
Very low.
Yeah, so alcohol has very low or high vapor pressure. Well, alcohols have a very high vapor pressure. So maple syrup has low because its intermolecular forces are strong. Alcohol has very high vapor pressure. Things with high vapor pressure are very volatile, like alcohol.
What about hydrogen?
Hydrogen's very
Very low.
high vapor pressure.
Very high.
We also have something called heat of vaporization, which is the amount of energy required to vaporize. So things that are really sticky are hard to vaporize and take a lot of energy. So maple syrup would have a high heat of vaporization, whereas alcohol would have a much lower heat of vaporization. Boiling point is the temperature at which the liquid turns into a gas spontaneously. And
Did you say you mean an alcohol that dissolved right away? So you mean like a very high concentration alcohol? Took a sip and evaporated really quick?
high concentration of alcohol, yeah, to evaporate quickly. That's what we used to do all the time. You know, there's different ways you could dry glass. One way is you could use a paper towel. Another way is you could wash off the water. We used to wash off the water with alcohol. You wash off the water with alcohol, and then you're just left with alcohol, and the alcohol just vaporizes
Set on
easily.
fire.
You could set it on fire too. But it's a quick way to dry it without having to screw with paper towels. You know?
And disinfectant.
Doesn't leave
But-
residue, that alcohol.
It doesn't leave
Would you have
any
to clean it up
residue.
first before you put anything in there?
It doesn't leave any residue because it has extremely high vapor pressure and it vaporizes easily. Oh, what was that?
Would you have to, like, when you did it, like, hook it up and then heat it up, like the glass?
No,
so
we
it
don't.
would vaporize
You don't have to
before you put
heat it
something?
up. You know, I have this. When I was working in the laboratory, I had a spray bottle of water, and a spray bottle of alcohol, and a spray bottle of acetone. And so what I'd do is I'd hit it with water first, and then hit it with either alcohol or acetone, just to dry it off.
You wouldn't contaminate it?
No, because it's so volatile, it has such a high vapor pressure, it completely evaporates off. You know, so it leaves it clean. There could be a residue, depends on what contaminants are on the surface, but most of the time there's no residue at all.
So anything that's thicker is harder to
Well,
bust?
if it has weak, like alcohol and acetone, they have weak intermolecular attractions. So if they're very volatile, they vaporize easily. They have very low boiling points. Things with low boiling points are weakly held. Things with high boiling points are strongly held together. When we look at the energetics of vaporization, here, it costs energy to vaporize molecules off the surface. They got to break free. You know, the other molecules are trying to stick onto them, so they got to break free. That's going to cost energy. That energy is called delta H of vaporization, or the heat of vaporization. And so this is the amount of heat required to vaporize a certain amount of liquid. The opposite is condensation, and it turns out that it's equal and opposite. That is, the amount of energy it costs to vaporize is equal and opposite to the amount of energy that's released when it condenses, which is exothermic. So it's endothermic in one direction, exothermic in the other. Heat of vaporization and heat of condensation. We're going to look at these in more detail at the end of the chapter. There are a couple of other properties. Viscosity, like the higher the viscosity, the slower it flows. So maple syrup has a very high viscosity.
So the
because,
thickness?
yeah, because of its thickness. The thicker it is, the more viscous it is. So alcohol has a low viscosity. It flows quite easily.
And water has a little viscosity?
Yeah, water also has a low viscosity. Surface tension. Maple syrup has a high surface tension. It's hard to break the surface of the liquid. Alcohol has a low surface tension. It's easier. All these things are related to the intermolecular forces, the forces of attraction. The intermolecular forces hold the water together. It's not gravity, the intermolecular forces that causes these to stick together. Surface tension is a result of the molecules. You know, what would you rather be? A surface water molecule or an interior water molecule?
Surface.
Yeah, you know, it depends. If you'd rather escape quickly, you'd want to be a surface, or if you want to be in the midst of the party celebration, you want to be in the interior, right?
It's supposed to be.
And it turns out that the interior ones are lower in energy than the surface ones. The surface ones are high energy. They're high energy because they're only held together by these. You know, there are attractive forces here. But whereas an interior one has attractive forces all around it, 360 degrees, this one's only 180.
Look at the outward ones. Something just goes, are those the atoms that are just outside of the.
Well, basically, this is why water tries to minimize the surface area. Water tries to minimize its surface area because the surface molecules are higher in energy. So when we look at a drop of water, what's the shape of a drop of water? It's a sphere. It's a sphere because we want to minimize the number of surface water molecules because the surface water molecules are higher in energy. And so it's going to cost you energy to flatten that water molecule out because it's going to create more. It's going to force more of the water molecules out on the surface. from the bulb or the interior. All right, I'm gonna stop here because we can look at some more.
Not anymore.
He used to play football.
I'll have your pencil here. That's why. I'll have it to you by tomorrow.
Or you know what you can do? You can buy pencils and they give me 2 for their tea list. Right? Sounds like a plan. We're laughing about this shit. Like, I'm not going to tell you what class you got. You know what? I'm going to buy you a couple pencils.
Bring it for my birthday.
When's your birthday?
Oh, you got something like
That's like the last thing. See if
Yeah.
I remember.
Yeah.
A pack of pencils and a pencil. Can you get this out?
And bring me a monster, that'll be great.
That's so fucking good.
Excuse me?
Your
second biggest part chemistry, but it's also
I'm saying like I might get
part
out.
biology. But what do you know like what atoms are like for like plants? Plants like they're all just made out of the same organic material that we are, right? Where does it all come from? Like matter can't be created, destroyed. Like how does one seed grow into like a big like where does that material come from?
Around it and then like
Around it? So all that was in the ground already?
You can't grow a tree with just water.
Exactly. If I was somewhere that
That's why fertilizer is very good. It's really rich in nutrients. That's why people use fertilizer.
so I just need nitrogen
American studies.
and you know the
Either you're taking English and or English, American
The
Studies,
service
have
living
one
laws for
A.
other laws.
Ew.
Either bio.
plants thrive with wherever there's carbon dioxide, right? They don't carbon dioxide.
Yeah, right.
They like carbon
They like
dioxide.
carbon dioxide.
Yeah, I know.
That's why there's a big thing
About like.
You're talking to who?
I know. I
to,
like
big
looking.
thing to,
Sorry.
I mean, I'm not bothered by it. It's okay. I'm just
Kathy
like,
is bothered by me having my phone out while he's like
I'm trying to create a system.
she like
A system
She like airdrops me pictures. Stop
trying
using
to,
your
but in my
phone.
head.
Oh my god.
Because then you're like, wait, I don't get it. And
Or
it's
if I
like,
create a
we
system
just
where-
learned about this.
Literally on the quiz today, I was like, hey, can you help me? She's like,
Or I can tell you.
And then she
if
leaves. She
I
just
was,
says,
if I had, let's say,
I didn't
yeah, I'm like in the
grab it.
ocean, like in the middle of nowhere, and
So,
I'm kind
BB
of
helped me,
detached from
so
like mainland.
Yeah,
and
because
then
BB's
I
like
was
awesome.
yeah, completely like independent.
BB's like so nice.
I was thinking I'd take the mealworms.
BB's
Mealworms
just-
could be a source of
BB's the
one of the
nicest
byproducts is carbon
I know,
dioxide.
she's so nice.
You could get all the carbon dioxide. You could like collect it and then put it like in a room full of plants, and then it would grow better, right?
Yeah, but at certain levels, there could be a point where there's too much carbon dioxide, then it might be damaging for the plant. You know, just like because plants have adapted to certain levels of carbon dioxide. So if it goes way too extreme one way or the other, it can adversely affect the plants. You know.
How about us? Because we breathe in oxygen. We need oxygen, but the
Yeah.
atmosphere is made out of mostly nitrogen.
Yeah, right.
So why would we?
Because we're adapted to breathing 20% oxygen.
That's what we like. We like 20% oxygen.
No, some people breathe higher percentages of oxygen than people who have decreased lung capacity. But we've been, you know, our lungs are quite capable of extracting, you know, the oxygen out from air.
That's just because we're adapting. But is
Yeah.
it possible just to adapt to lower oxygen?
Yeah, I suppose, yeah, people do it all the time. They get more red blood cells. So if people do high altitude training, they get lower oxygen.
That's for does elevation mass.
They generate more red blood cells that can